Okay, and now, what is the moment of inertia of a disk? So, moment of inertia depends on how you define your moment. So, now the simplest is to have the moment be perpendicular to the disk, going through the center of the disk, and so the disk is spinning about that moment. And so that's the easiest moment of inertia to calculate. So for discrete masses, oops, I don't even know what that is. It's the sum over all your masses times the distance from those from your z here, or your moment, squared. But for a continuous mass, such as this disk, then we're going to use the integral like this. So you integrate over the entire mass, multiplying by the square of the distance from your moment. To solve this, we need to know what our mass is. So assuming again that it's evenly distributed across the entire mass, then the total mass is going to be the density, or the area density, I should say, times the area, right? Or the area density will be the mass over the area, okay? And the area of a disk is pi r squared, where r is the radius of the disk. Okay, so now to solve for our moment of inertia, we need to identify a piece of the disk that we're going to be integrating over, or our form of integration here. So if we consider a small ring at some distance r from the center, and the width of this ring is dr, then and the easiest way to visualize this is not actually to look at the ring, but to extend the ring out. And so the width of the ring is dr. And what's the length of the ring? Well, the length is just the circumference of a circle at a radius r. So that'll be 2 pi r. So that means the area of this ring, dA I'm going to call it, this small area, is 2 pi r dr. And now we can convert this small dA to a dm using our density, right? So dm is just sigma dA, which is then 2 pi r sigma dr. So there is our mass element that we're going to be integrating over. I'm just going to migrate that up. Okay, so putting this back into our moment of inertia expression, we now integrate, and our integral now is going to be over r, so it's going to be from 0 to r, the complete disk. And that'll be just r squared times our dm, which is 2 pi r sigma dr. 2 pi and sigma are just constants, so they can come out front. And the r will give us a 2 pi sigma integral 0 to r cubed dr. So the integral of r cubed, we can just use the power rule, so that the 3 goes up to a 4, and then we divide by 4. And so that's 2 pi sigma r to the 4th over 4 from 0 to r. And at 0, r is going to be 0, so the whole expression will be 0. So then our moment of inertia is 2 pi sigma r to the 4th over 4, or canceling the 2. Or canceling the 2. Pi sigma r to the 4th over 2. Now we can clean this up a little bit because from before we have that our area is pi r squared and our mass is sigma times our area. And we can see here that pi r squared is in here, leaving an r squared, and we still have that sigma lying around. So sigma pi r squared is our mass. And so using those two expressions, we have that our moment of inertia is mr squared over 2. And this is neat because these are just parameters for the disk, right? So this is the total mass for the disk, that is the radius of the disk, and it's just divided by 2. Slightly more difficult, and remember this is the moment of inertia for a disk which rotates about a moment which is perpendicular to the disk, so you're spinning the disk. Considerably more difficult would be to compute the moment of the disk along a moment arm that goes this way. So now to do that, we would have to consider elements this way, because the r is always the perpendicular distance, right? So that's our r. And so then the question is, how does this length change with r, right? Because we need to calculate r squared dm. And the best way for us to get what our dm is in terms of our r is through our area expression. So we need to find some dA, and our dA in this case, again, our best chance at it is to have these length of our expressions multiplied by dr, because each one of these little things has a width of dr. And we can do this using just some geometry. And so if we look at one particular one, and we consider this to be a straight line, a distance r from the center, then that and that is definitely r, which means that this length is r cos theta, where theta is this angle in here. And now I've kind of switched to a theta, but it turns out that trying to calculate this in terms of r actually becomes quite difficult. And so switching to theta makes things a little bit nicer. And our relation for our r here now is that r is, so this is the hypotenuse of our right angled triangle, which I've drawn here. R squared minus r squared cos squared theta, or r equals r square root of 1 minus cos squared theta, which means it's r sine theta, which, I mean, we could have figured out anyway. So using that for our r, and using our length now, so now we just need to, I've got two d's there that I didn't notice before. Using that for our r, using our length as 2r cos theta, representing our, and now we need to turn our dr into a d theta. So dr is r cos theta d theta, just by taking the derivative of this expression. Okay, and there's our r, as there's two of them, or there's our length, as there's two of them. That means that our dA expression is now 2r squared cos squared theta d theta. And that means then that our dm is still just sigma dA. So we just multiply this expression by sigma. And now we're finally in a place to start our integral. I equals integral r squared dm, where now we just move everything over. So this is going to be, our r is just r sine theta, so there's going to be r to the fourth. I'll just keep the integral there. Sine squared theta. Actually, I might as well just do everything explicitly. So r squared sine squared theta for the r squared, and then our dm is sigma times 2r squared cos squared theta d theta. And our d theta integral is going to go from 0 to pi over 2. Right, so 0 would be it pointing along the arm, and then it pointing along this arm, and then pi over 2 would be straight up. And remember, I've already doubled the length. And the only other thing to consider here is that only covers half the circle, so our moment of inertia will actually be twice this, because we need to consider the other half of the circle. So we need to double the whole thing. And then continuing this forward. So I'm just going to clean up things a little bit. So pull the constants out of this expression. So there's a sigma, a 2, which I multiply by the other 2. So those 2's, the sigma, and then the r squareds can come out. So that's r to the fourth. And then it's an integral from 0 to pi over 2 of sine squared theta cos squared theta d theta. And that should be pi over 2. This integral is not easy to solve, so I ended up just looking this up. So most integrators or most integral tables of integrals will have this. And so then this is 4 sigma r to the fourth. And the indefinite integral here is 1 over 32. 4 theta minus sine of 4 theta from 0 to pi over 2. And now if we look at this expression, we can simplify without really writing out or doing too much math here. So 4 times pi over 2 is 2 pi. So sine of 2 pi is 0. Also at the other end, sine of 0 is 0. So that means this quantity here is going to be 0 at both limits, so we don't even need to worry about it. And theta, when theta is pi over 2, this will have an actual value, but when theta is 0, that is going to be 0 as well. So that means this end of the expression we don't really need to think of either. So then all that's left is the pi over 2. So that means the whole thing is 4 sigma r to the 4th times 1 over 32 times 4 times pi over 2. And now we can start to pull some things out. So 4 times 4 is 16, 32 times 2 is 64. I'm just going to migrate. over 64 sigma r to the 4th. And then that's just a quarter. So it's sigma r to the 4th over 4. And again, from before, our entire mass is pi r squared, and I dropped a pi, so there should be a pi in there and a pi in there. Right, so there's that pi I dropped. Pi r squared sigma. So there's our sigma pi r squared, and so then our moment of inertia is mr squared over 4. And so again, so now in this case, this is the moment of inertia for a disk rotating about a moment arm that lies through its center. So just to wrap things up, right? So we had a disk with the moment arm running through the middle and along one of the diameters of the disk, and the I was mr squared over 4. And then we also considered a disk where the moment arm was perpendicular to the disk and running perpendicular to the radial line, and that was mr squared over 2. Okay, so depending on how you set up your moment arm, you're going to get a different moment of inertia. Okay, so then if you look at the solution here, most likely, so it's just the integral, and quite a bit of the math is gone through here. And so this is for only for this case, but that's fine. It wasn't specified in the question. So I just added a couple extra things. So it's good.